This is Euclid Book 2, proposition number 13, and there is only one more proof after this, and then we'll conclude Euclid Book 2 completely. Then we'll move on to Euclid Book 3, where things will get really fun. Alright, first of all, Euclid wants you to draw an acute angle triangle. Well, we have one here, ABC. And this angle right here is acute, and you should know what acute angles are by now. Alright, and then he wants you to draw a line from point D to point A, and it has to be perpendicular to line BC. And if we do this, we now have a right angle. Okay, so we're going to have two right angle triangles, ADC right here and ADB right here. Okay, so what does Euclid want us to do? He wants us to prove that the square on AC, which this would be one side of a four-sided square on AC, okay, is less than, the area inside of it is less than the area of CB. Well, CB is right here, so if we were to draw the square of CB, that would be this area right here, okay, plus the area of BA, which this is BA right here, the area of BA, okay. So the area inside of square AC is going to be less than the area of square of CB and the square of BA, and the amount less is going to be twice the rectangle of CBBD. Well, here's CB here, okay, CB and BD. Okay, so if we were to make a rectangle with one side CB and the other side BD, we'd have a rectangle right down here. And we can go on, but let's just save the whole thing for the end of the proof. Okay, now, we know that the square of CB, okay, there's a square underneath here, plus the square of BD, okay, is equal to twice the rectangle of CBBD, which I already talked about, plus the square of DC. Well, DC is this part right here, okay? And this is all possible by Euclid Book 2, proposition number 7. Alright, so what Euclid wants us to do next is he wants you to add the area of square AD. Well, here's AD right here, and the area inside of AD, well, we can form a square with one side being AD and the other three sides being the same size as AD. We'd have a square right here. We've done this many, many times before. So, the square of CB plus the square of BD plus the square of AD equals twice the rectangle of CBBD plus the square of DC plus the square of AD. Now I'm going to go through this one more time a little more slowly. The square of CB, the area inside the square of CB, added to the area inside the square BD, added to the area inside the square AD, is equal to twice the area inside of CB times BD, okay? So you're going to have a rectangle, and one of its sides is going to be CB, the other side is going to be BD, and of course you're going to have the other two sides equal to that. Boom. Alright, so twice the area of CBBD plus the square of DC plus the square of AD. Okay? Now, the square of AB is the sum of the square of BD and AD. Now what that means is that the area inside of AB is the same amount of area that you would get if you were to add the area inside of BD plus the area inside of AD. Okay? And we can say this because of Euclid Book 1, proposition 47. And we can go on to say that the area inside of square AC is equal to the same amount of area that you would find if you were to add the area of AD plus the area of DC. And of course this is again possible by Euclid Book 1, proposition number 47. So Up here in this top equation, we had the square of BD plus the square of AD. We're now going to replace that with the square of AB. So, the area inside of square CB, okay, let's say that again, the area inside of square CB plus the area inside of square AB equals twice the area that would be found between CB and BD plus the area found inside of square AC, because we're replacing AD and DC, the areas inside of AD and DC, with the square of AC. Alright, so that means that the area inside of square AC is less than the area inside of square CB plus the area inside of square BA, and it's going to be less by twice the area of CB times BD, which is what was required to be proven. Alright, now I will tell you more in a future video, so stay tuned.